In this video, we're going to take a look at exponential functions and how they can be used to model real-world situations that come up. So in example 1, it says, suppose there are initially 10,000 bacteria in a culture and the population doubles every 3 hours. So to start with here, we know we're trying to come up with a function, right, p of t. And with exponential functions, we always start with our initial amount here, right? Now, since we're doubling every 3 hours, one way to think this through would be to say, every so often, I want to double my initial population, right? Okay, well, I want to, if you think about it, we want to times by 2 when t is equal to 3, right? After another 3 hours, when t equals 6, we want to times by 2 again. So in other words, we want to times by 4, right? Or 2 to the second power. And when t is equal to 9, I want to times by 2 yet again. So that means overall times the initial population by 8. So that's t to the third. And so if we look at the relationship between this exponent here, and I can put a little 1 right up here, and the amount of time that's gone by, we're just dividing the time by 3. So that tells me that I just put a t over 3 here for my function value. So then it asks me, when will the population reach 30,000? Okay, well, I can put 30,000 in for p of t. Set that equal to 10,000 times 2 to the t over 3. And then, of course, we have worked with solving exponential equations enough now that we know that we want to try to isolate this exponential first. So I'm going to go ahead and divide by 10,000 to get the exponential part on the right side all by itself. And so I end up with 3 is equal to 2 to the t over 3. And then we know that to get that t, we're trying to solve for how much time has gone by. We've got to take the natural log of both sides so that I can use the power rule to get the t out of the exponent. So the natural log of 3 is equal to the natural log of 2 to the t over 3. So the natural log of 3 is t over 3 times the natural log of 2, bringing that exponential or that exponent down. And then, natural log of 2 and 3, those are just numbers. So if I multiply by the reciprocal of the natural log of 2 over 3, so I multiply by 3 over the natural log of 2, 3 over the natural log of 2, then everything cancels out here on the right side. And of course, this is an application, so instead of worrying about getting the exact form of the answer down, let's just go ahead and put all that in our calculator. And when we do, we should get 4.75 hours have gone by, right? And if we know that we have times the initial by 4 after 6 hours, so that would be 40,000, and after 3 hours, we're up to twice 10,000, so 20,000. So then we should be at 30,000 somewhere in between 3 and 6 hours. So that seems to bear out what we would expect to happen. And then part C says to rewrite the function in this form with e to the rt. And so remember, the reason that we might want to do this is that when we have it in the form a e to the rt, then it's in that continuous growth rate form. And if you think about bacterial growth, you would kind of expect that to be happening more or less continuously. So instead of how we framed the function before, we want to write it as a times e to the rt. So we just need to find what r is. So I can take my 10,000 times 2 to the t over 3 and set that equal to 10,000 e to the rt. And of course, I can quickly get rid of the 10,000s on both sides by dividing. Those are going to be irrelevant. So we have 2 to the t over 3 is equal to e to the rt. But of course, we can get this r out of the exponential if we take the natural log of both sides. So we'll do that. So over here, we can bring the t over 3 down in front. And then here, yeah, it comes down front, but remember that if you take the natural log of e to an exponent, you just get the exponent back again, right? They're inverses of one another, so they undo each other. So to finish solving for r, we just multiply by 1 over t on both sides, which completely eliminates t from consideration, which is a good thing. So what we get here is that r is the natural log of 2 divided by 3. So what we can say is that p of t, sorry about that, p of t is equal to 10,000 e, and then r, and it's always best to leave it exact, so I'm not going to type that in the calculator. I'm just going to leave it like this. Natural log of 2 over 3, that's my r, times t. So this function and this function here, they're the same function. They're just expressed differently. But what I can say is that this is my r, right, the continuous growth rate. And now, even though I want to keep it exact in the function itself, let's go ahead and figure out, approximately what is this equal to. It's equal to 0.231. So in other words, we have a continuous growth rate of 23.1%. All right, so let's take a look at another example here. It says that a town's population is increasing at a continuous growth rate of 13%. When will the population be double what it is currently? Okay. In other words, what is the doubling time of this population? So this time it's kind of backwards of the last example. In the last example, we figured out our continuous growth rate at the end. Now they're giving it to us right at the outset. So what that means is that I am going to start off understanding that I have this population function, and I'm going to write A, the initial amount of the town's population, and I don't know it, right? So I'm just going to leave it as A, but I'm going to write E to this is my R, my continuous growth rate. So E to the R, so 0.13 T, right? So if they give us the continuous growth rate, we know that is the R value that goes up here in the exponent of our base of E. So when will the population be double what it is currently? Well, when it is double our A value, our initial population value. And so we can see that A, whatever A was, it is not really important, right, as to how long it takes the population to double. So we have 2 is equal to E to the 0.13 T. And as we did in the last problem, we need to solve for our t. So this is the natural log of 2 is equal to the natural log of e to the 0.13 t. But that is just the natural log of 2 is equal to 0.13 t. And we can get that by itself. So the natural log of 2 over 0.13 is equal to t. So that's our doubling time right there. So to write this a little differently in part B, it says, what is the relationship between the continuous growth rate r and the doubling time? Well, our continuous growth rate was this 0.13, right? So in this problem that we just did, the doubling time, right, which is our t value right here, is the natural log of 2 divided by our r value, right? That was the r that we started off with here. Now, what we can also do is, if I go back to that previous example for a moment, in that previous example, r was equal to the natural log of 2 over 3. But remember that 3 was the doubling time in this particular instance, right? And so if I go back here, if you just solve this little equation for r, then we can also say that r is equal to the natural log of 2 over the doubling time. So this is worth remembering. So if a question asks you for the doubling time, and you know the continuous growth rate like we did right here, then you can just plug that continuous growth rate into this little formula, and that'll give you your doubling time. And alternatively, if you know your doubling time, you can get your continuous growth rate right away just by taking the natural log of 2 divided by whatever that doubling time is. All right, so those were 2 looks at exponential growth. So let's look at exponential decay. So a common example of this is looking at radioactive substances, right? So we know that a radioactive substance decays over time and it emits radiation, and that's why in certain circumstances it can be kind of problematic, because the radiation it leaks can be damaging to biological organisms. So when we talk about exponential decay, rather than talking about doubling time, how long something takes to get twice as big as it started, we're going to talk about half-life. How much time does it take to have half of what you started with left over? All right, so in this, here it asks us, how does the continuous decay rate r of a substance relate to the half-life? Okay, so I'm going to start off again. If I want to know, say, the amount of a substance that's left over after a certain amount of time, we're still talking about an exponential, but it's a decay, right? So my r would be negative instead of positive. All right, so here's what they're asking of us. They're saying, how long would it take to have half of what you started with? Right, so I could take 1/2 of what I started with is equal to this exponential function. And, I have an a on both sides, right? So if I divide by a and divide by a, I get those to cancel out. So I get 1/2 is equal to e r to the rt. And I can take the natural log of 1/2 is equal to the natural log of e to the rt. So on the right side, of course, the natural log and the e kind of zap each other, so I get r times t, and just like I did in the last problem, I can solve for t, and we can say that t, which is the half-life, how much time it takes to have half of what you started with, is the natural log of 1/2 over r in general. So, and let's just call it h. Half-life is, yes, the natural log of 1/2 over r. Sometimes you'll see it written this way, though. You'll see it written as the negative natural log of 2 over r. Now, where that's coming from is that the natural log of 1/2, I think we can all agree, is the same as the natural log of 2 to the negative 1, right? Bringing the 2 up and making the exponent negative. But then the power rule says that you can bring that negative 1 out front and say it's negative natural log 2. So it's just saying that natural log of 1/2 and negative natural log of 2 are the same thing. So you'll see it written both ways. So just be comfortable with both. And then similarly, we can say that our continuous growth rate is the natural log of a half over the half-life, or if we prefer, the negative natural log of 2 over the half-life. All right, so let's take a look at an example with some actual numbers to take a look at. It says the half-life of carbon-14 is about 5,730 years. If a piece of petrified wood contains 30% of the carbon-14 it should have had when it was alive, how old is the petrified wood? So what I can do is avoid trying to reinvent the wheel, right? So I know that my function here is going to be something like this. A of t is equal to 100 e to the rt. Okay, what's 100 all about? So A of t is going to be the percent, right? Percent of original substance left. And so, of course, 100 would be the initial percentage, which would be 100%. Okay, because they're talking about things in terms of percents here. So this is going to be the form of my equation. Now, what I am allowed to do now, because of what we just discovered, is if I go back to that previous example, we already know, right? We already know what form R should take on, right? It should be either the natural log of a half divided by the half-life or the negative natural log of 2 divided by the half-life. I kind of like this one, though, because it reminds me that it's decay by having the negative out front. So I'm just going to jump straight to saying A of t is 100 e to the negative natural log of 2 divided by the half-life, which they told me is 5,730 years. And then, of course, I multiply by t. So to figure out, okay, when do I have 30%? I just put in 30 in for my amount. And set about solving for my t. So I can, of course, get rid of this 100. So we have 0.3 is equal to e to the negative natural log of 2 over 5,730 t. And we know the routine by now, right? Take the natural log of both sides. And so we end up with the natural log of 0.3 is equal to negative natural log 2 divided by 5,730 times t. Right? But again, this is just a fraction times t, right? So if I want to get rid of it, I can multiply both sides by the reciprocal. I'll change colors to make it a little nicer looking here. So we'll have times negative 5,730 over natural log 2 and negative 5,730 for natural log 2. So of course everything cancels out here and we end up with t on the right. And here we kind of have a mess, but it's a mess that we're just going to end up putting in our calculators anyway. And if at first things seem a little funny because you have this negative here, the thing to remember is the natural log of a number that's smaller than 1 is going to be negative also. So the two negatives will multiply to make a positive, and so we will get a positive time just like we know we should. So putting that in our calculator, we get something like 9,953 years, something like that. All right, so another different type of example we're going to take a look at here is what's referred to as Newton's law of cooling. Okay, so here's the formula for Newton's law of cooling. So the temperature of some sort of object is going to be equal to the temperature of your surroundings plus this A times e to the kt. Okay, so what is all this? Ts is, like I said, is the temperature of your surroundings. A is a constant that is determined by the initial temperature of the object, and we'll see exactly how it's determined in a moment. And then K is a constant, and it's just the continuous rate of cooling of the object. And of course, T is time. All right, so let's kind of work this out here. It says a bottle of juice initially has a temperature of 70 degrees. It is left to cool in a refrigerator that has a temperature of 40 degrees. After 10 minutes, the juice has a temperature of 64 degrees. When will the temperature reach 45 degrees? Okay, so there's kind of a lot here. So first, let's fill in what we definitely know. They told us that Ts is the temperature of the surroundings, and we can see, we know that, right? The surroundings is going to be the refrigerator. So I can immediately put T of T is equal to 40 instead of Ts. But I don't know A yet, and I don't know K yet. So I'm going to need to know both of those things before I can answer this final question here. Now, they did say that the juice initially has a temperature of 70 degrees, so that, in other words, when no time goes by, when T is 0, right, the temperature is 70. So that means I can put 70 in for the temperature at the same time I put 0 in for T. So this will be 70 is equal to 40 plus, well, this will be A times e to the 0, which of course is just 1. So what we get here is if we subtract 40 from both sides, 30 is equal to A. So that's good. We've made some progress there. Now, if we are a little observant here, notice that A ends up being your initial temperature minus the temperature of the surroundings. So it's the difference between those. So what you can do is you could, for A, just make a little note that A is equal to initial minus the temperature of the surroundings, okay? And then you wouldn't necessarily have to do this every single time. But at any rate, we know now that that's 30, so kind of updating where we're at, the function is T of T is equal to 40 plus 30 e to the kt. So now we need to know K, right? But that's what they gave us this information for. After 10 minutes, the juice has a temperature of 64. So if I plug 64 in for the temperature at the same time that I plug 10 in for T, then I'm going to be able to figure out what the K is, the continuous rate of change in the temperature. So I'll subtract 40. So we have 24 is equal to 30 e to the 10k, just kind of flip-flopping the order there. And I can isolate my exponential. So this is, I suppose I can do a little bit of reducing here. Let's see, 6 goes into both of these, so this is going to be 4/5 is equal to e to the 10k. So if I take the natural log of 4/5 and the natural log of e to the 10k, we end up with 10k is equal to the natural log of 4/5. So dividing by 10 on both sides, we figure out what our k is. So overall, we now know our function, right? T, the temperature, capital T, as a function of little t, the time in minutes, is going to be 40 plus 30, and this is going to get a little tough to write all on the exponent, the natural log of 4/5 over 10 times t. So just replacing this with my k. And so now I've got the function. All right, so then they're asking me, when will the temperature actually reach 45 degrees? Kind of separate this out here. So now we're finally, after all that, in a position where we can answer their question. So it took quite a bit of work just to figure out exactly what the function looked like. But now I can go ahead and I can say, all right, 45 is equal to 40 plus 30 e to the natural log of 4/5 over 10 times t. Oops. So we can subtract 40 from both sides. So we have 5 is equal to 30 and all that stuff here on in the exponent. And we can divide by 30. And 5 over 30, dividing by 5 on top and bottom, gives me a 1/6. And I know that the algebra on these can be a bit of a pain. So let's do what we have done many times now and go ahead and take the natural log of both sides of that equation. And we know that on the right side here, we're going to get the natural log and the e to kind of cancel out, right? So this will be the natural log of 1/6 is equal to the natural log of 4/5 divided by 10 times t. So we multiply by the reciprocal on both sides to get that t all by itself. And while the solution over here on the left side is going to look like kind of a mess, we of course are going to be just interested in approximately what this is equal to. So 10 times the natural log of a 6 divided by the natural log of 4/5 is the solution we're looking for. And so what we get there is that t is approximately 98.3 minutes. All right, so in example 6, let's suppose the number of words per minute achieved by a beginning typer as a function of the number of weeks of practice is given by the function 70 minus 60 times e to the negative 0.3x. So what we're going to do here is I've given us a function, and let's see if we can interpret the important parts of it. So it says find and interpret the vertical intercept, right, or the y-intercept. Okay, so let's remember first of all that the vertical intercept is when x is equal to 0, right? X equals 0. Now, when you're talking about a linear function or even a quadratic function, a lot of times you just kind of get lazy and say, well, it's just the number of the term that doesn't have an x in it. But you can't do that with exponentials, right? So if I take f of 0, I put a 0 in for my x, but understand that doesn't get rid of the 60, it just makes the e to the 0 equal 1, right? So I end up getting 10 as my answer. So what this is saying is that when no time has gone by, this typer can do 10 words per minute, right? Or we could say initially, the typer has a speed of 10 words per minute. Now it says find and interpret the horizontal asymptote, right? Now we looked at horizontal asymptotes with rational functions, right? So a horizontal asymptote was what happens when we let the x value get really, really big, right? So let's think about this for a moment. So first of all, f of x, right, is equal to this. But it might also help if we realize that if I have a negative in the exponent, I can make that positive if I put it in the denominator. All right, so looking at it like this, let's think about what happens as x gets really, really big, or as x goes to infinity. What happens to f of x? Well, over here, the bottom gets really, really big. So I have 60 divided by a really, really big number. And if I take 60 divided by a really, really big number, like 60 divided by 1,000,000, we know that that number is getting really close to 0. So this, right, approaches 0 when the x gets big. So as x gets really large, we know that f of x gets close to 70, right? Because that second term there with 60 over e to the 0.3x gets close to 0. All right, so what does that mean? So the more, right, the more the typer practices, the closer the typer speed gets to 70 words per minute. Or another way of thinking of it is kind of no matter how much this typer practices, the typer's not going to get above 70 words per minute because it's just at some point your fingers just can't move faster than that. All right, so now let's look at part C. It says how many words per minute will the person be able to type in 4 weeks? Okay, so notice that this is a function of the number of weeks, right? So 4 is what belongs in there for the x. So I'm just saying f of 4 is 70 minus 60 times e to the negative 0.3 times 4. And we can just type that in the calculator and we get 51.9 words per minute. And then part D, how long will it take for the person to be able to type 60 words per minute? Okay, so that means we can say, well, I know that I'm shooting for 60 words per minute. So this is going to be 70 minus 60 e to the negative 0.3x. Right, but this looks a lot like the type of equation we just solved in the Newton's law of cooling problem. So we have negative 10 is equal to negative 60 e to the negative 0.3x. And as we've done many times, isolate that exponential. So reducing negative 10 over negative 60 to 1/6 e to the negative 0.3x. And taking the natural log of both sides. And then to finish it out, divide by negative 0.3. And so when I type this in my calculator, I get about 5.97. So I'm just going to go ahead and round that to about 6 weeks.